Well, here goes nothing. Um, Welcome everybody to today's live stream. My name is Aaron Magnan. I will be talking about a video that I linked in the description. If you haven't seen it yet, I would wait until after the live stream to watch it. But in it, this very interesting group at Brigham Young University is like making these amazingly cool devices, these compliant mechanisms. And when I watched the video, I was like really interested in how I could use finite element analysis to learn more about the systems, to maybe test them for myself, or to vet them to make sure that they're going to do everything that was claimed in the video that I'm referring to. Online with me today, I have Brad Tallis. We've swapped roles a little bit. Usually he's presenting and I'm the one who's answering questions, but he's over there. Looks like we have a good number of people here, and just to give you a little understanding of what we're going to be doing today, we're going to take the files that this team has shared with us, and we're gonna build them in Fusion if need be, and then we're gonna put everything together and run some simulations. And I'm going to do a little bit of mesh work, a little bit of importation from DXFs and various other things, but I think that just about does it for what I wanted to talk about in the intro. I actually have notes today. My last presentation, I got to apologize a little bit. It was a little disorganized. I kind of got thrown into that a little bit late. So hopefully today goes a little bit better. One of the things I wanted to do was avoid saying things like but I've already messed that up. Anyway, so here's the screen, or here's the video that I'm referring to. And as I mentioned, if you haven't seen it yet, go ahead and watch it after today's video presentation. But in it, and I'll just kind of skip through a couple spots, this team at BYU talks about these compliant mechanisms, and they're doing all kinds of really neat stuff with it related to the medical industry, as well as like space exploration. I would highly recommend that you jump over to their website, compliantmechanisms.com, byu.edu. Learn all about the amazing team that's behind this. And what I will be doing here, and the reason why I have this showing for you, is that I wanted to make sure that you can see that there's these resources and maker resources. So if you wanted to grab these files and do just like I'm doing, bring them over to Fusion 360 and run simulations, or more likely, if you have a printer, you're going to print them and keep them around your house to show off to people, then that's something that you can do. So just jump over to those maker resources, and essentially this is going to link to some Thingiverse locations where you can actually pull down and download these files. So without further ado, let's talk about how we're able to bring these files into Fusion 360 for use for these simulations that I'm referring to. So let's just jump over to Fusion, and here I have one of the products I'll be looking at a little bit later, but I'm going to actually go and I'm going to create a new design here. And to do this, as mentioned, I'm going to use the files that I downloaded that they've so graciously shared with us, and I'm going to go ahead and I'll do the first one here, and the first one I'll use an insert from DXF, because for most all of the models that they showed and that they demonstrate on their website, they actually provide DXFs, so this cuts down a lot of the work that you would otherwise have to do. All I'm going to do here is I'm going to select the plane in which I want to drop this into, and I'm going to go and find the DXF I like to use. So not quite from that folder. We'll jump up one level here, and here's where I download the whole gamut of different products that I'll be looking at. The ortho-planar spring that I showed you just for a second there, the bistable mechanism, the bistable switch, the elephant that I found was so interesting and cool, and we'll be doing a little case study on it in the pliers that they actually spent a lot of time talking about in that video. But I've kind of pulled out the two files I want to use just to avoid having to sort through all those. And we'll go ahead and open up the elephant. And once I select open, it's going to go ahead and bring over that DXF for us to use. And what's neat about these DXFs is that sometimes they include, other details, like the pivots are actually on their own DXF layers, which is handy for understanding, why this mechanism works in the way it does. However, if I'm going to go and I want to extrude this, then I don't necessarily want those pivots, so I'll use this nice ability to turn off the pivots and maybe turn off, some of the other details, and I'll keep that up there to represent BYU for their hard work on this. And with the DXF, one thing you got to pay attention to is, what unit system you want to use. And I'm going to be using a lot of inches today. We get a lot of flack when we use inches, and I don't understand it. It's so easy to change. I mean, you just jump over your document settings. You can change it very easily there. But let's go ahead and now turn this DXF sketch essentially into an extruded solid, because we'll need that to be able to simulate it. So I'm just going to hit E on my keyboard, and then I'm going to be able to select, the different profiles that I'd like to extrude. So in this case, it looks like I need to select 3 different profiles. And then I'll just pull it up a small amount. And I don't want to go too thin here. I mean, if you're actually going to go and print this, you may want to save material. But in terms of the simulation I'll be running, if it's super duper thin, then it's going to cause me to have a lot of mesh elements. And so with that in mind, I'm going to maybe go to like a 1/4 inch thickness. And, if we're printing this on plastic, that's hopefully not going to use too much material there. What's really neat about these compliant mechanisms is that, you can go and extrude this. You can make hundreds and thousands of these in a very short amount of time, and they can do some really neat stuff. So there you go. There's one importation, and I'll go ahead and I'll just save this real quick. I'll come back and revisit this. I'll actually be setting up one of the simulation studies on it and using that to demonstrate. Looking at some of the comments, anyone else seeing the blurry picture? I just, picking up on, make sure I'm not doing something wrong here. Next, I want to go ahead and bring in another one of these designs that I'll be using a little bit later. And in this case, this was actually the only one that didn't include a DXF. And so what they did include, however, is the STL, which is great. You can go and print it directly from the STL, as you well know. But instead, I'll have to create this infusion in a different way if I wanted to simulate this. And some other people are saying it's a little blurry. Hopefully it's not the feed, but I'm going to keep an eye on that, make sure that we're not having other problems. As mentioned, I do want to go and I want to insert this next one as a mesh because it's provided in an SVG. And just like that, we now have, and I'm seeing more people saying it's blurry. That's unfortunate. I don't know. I'm not doing anything different here. Check my resolution. I don't know. Okay, bear with me. Hopefully it resolves. I don't know if it's a bandwidth thing or what, but as I was mentioning, this other particular case, we were not provided a DXF, so I'm going to instead have to bring it in as the STL that was provided. But if you've ever worked in STLs, and again, one of these things where you want to pay attention to the unit type, and when you're first dropping it in, you can flip the directions and adjust. I'm going to click OK, and that's going to drop in that SVG. But as I was saying, SVGs are, sorry, that's not an SVG, that's a STL. STLs are not great. Meshes are not great for anything simulation or design related. If I wanted to make a design change to this, I'm going to have a lot of problems. So one thing that we can do to try to convert this into a solid is to use some of our mesh importation tools. And I did a live stream on this a little earlier, but I'm going to show you a little bit of this in this presentation as well. Partly because we've kind of keyed how this is actually done. As mentioned in the last live stream that I did, I talked about the what's new stuff, but we moved this create mesh section tool into the create dropdown, so you don't have to go dig down into a sketch to find it. When you're here, all you need to do is select a sketch, or sorry, a mesh, and then you can go and rotate it around to capture the cross section that you're going to want. And in looking at this model, this cross section is most definitely the one that I want to capture. Okay, so let's see, and let's move on to how we're going to actually be able to use that now. So if I go and I hide the mesh body, these mesh sections are not necessarily something that you can extrude with, unfortunately. You can't just hit E and select the profile. There's actually no profile in there to select. So we have some tools to try to convert this into a more usable sketch. So I'm going to go and I'm going to edit the sketch that now contains that mesh section. And from here, from within the mesh dialog and the mesh tools, I'll be able to find this drop down here to find fit curves to mesh section. So here we go. I'm going to select the fit curves to mesh section, and as I scroll over, I'm going to be able to try to convert this. And so there's a lot of conversion tools you have access to when using this. The cheapest and dirtiest way of doing this is doing this closed spline, but it's not going to work well for anywhere there's sharp corners. And so if I scroll over it, it's going to give me a preview of what it even looks like, and you can see where it deviates from the mesh section that I have there. So one area in particular is like down here. You can see there's a pretty massive deviation. Up here there's a pretty significant deviation. And if I'm going to simulate this, there's particular areas that I want to pay a lot of attention to that I don't want to like modify, right? So I want to make sure that I keep the thickness here. I want to make sure it has significant strength there because I'm sure they've vetted this design quite a lot. I want to make sure maybe it closes off properly there. So before I go and do the shortcut method, I can do some normal like straight line fit curves. So I'll select this guy, and what this allows you to do is select right from the mesh section and create like a straight line. I just created a straight line. I'm going to click OK, and you'll actually notice that I do that quite a lot, and I can hide the mesh section. You can see what I just did there. I just drew in one basic single line. Sorry about I've been noticing this with the mesh sections. It does some weird like artifacts, something related to like where nodes intersect or something like that. But so if I really wanted to capture this, I would do this a couple times, and you'll notice that I actually exit out of this tool and like go back into it a number of times, and that's because I've kind of been burned a couple times. Like if you go and you select a number of these items, I'll click OK because I don't want to lose that selection. Sometimes I'll, for whatever reason, I keep losing it because I'll like exit out or hit escape or something, so I'll lose those important details that I'm trying to define here. And you'll see I'll use that nice right-click menu to re-access that same tool. And so essentially I just want to pull off a couple of these straight lines. And you don't necessarily need to use this tool. Some people might just prefer to use a sketch, but the problem with using just a normal sketch is that it's not going to snap to that mesh section, right? So I mean, I can sketch a lot faster just using this, but as mentioned, it's not going to capture that those points. It's not going to snap to those points, unfortunately. So with that done, let's go and do the fit curve, and we'll do the quick and dirty method. And because I've dropped in some of those additional lines, when I go to extrude this, I'll be able to capture this geometry a little bit better. I'm not going to deviate here because now I can select that area that I've included by creating that sketch. You can see here it's not going outside of that line. That's another benefit of me dropping in a couple little sketch lines. And for something like this, accuracy is not like crazy important, right? But for design, if you're trying to copy it, you're gonna spend a lot more time doing that. Essentially, is what I'm getting to. So let's go ahead and extrude this out. And again, I can do it like to a 1/4 inch, and essentially what I want to avoid is just an uber thin design, because that's going to cause me a lot of issues if I'm going to mesh and solve this thing a little bit later. So I hope that was handy. It sounds like I'm looking at some of the conversation. It sounds like the blurry is now fixed, or getting better at least, and I apologize about that. So now we've brought a couple of these in. Let's go ahead and move on to actually testing that. And so one thing I wanted to do here was I wanted to show one of the claims that was made, or one of the the questions that was posed by the man over there, Larry Howell. And I'll just play a video real quick so you can see, get an idea of what I'm going to get to. So
okay, I'm going to push on the elephant's rump this direction. Okay, I'm going to hold this, and that little dot right there is that dot, when I push on it, is it going to go left, right, up, or down?
Okay, so I hope the audio worked with our broadcasting software OBS, which we love, by the way. I highly recommend it. Um, I don't actually hear the audio, so I assume it played. It says it's playing, but on my end, I don't hear it, so it's just part of the broadcasting thing. But my question to you now is, and if you've already seen this, please don't answer. But if you haven't seen the video and know the answer to this, which way do you think that trunk is going to move when the forces are applied at the back end of the elephant? And Brad's telling me it worked. Thank you, Brad. So is it going to move up, down, left, or right? And I might as well bring this model up and show you. We're looking at the end here, the end of this trunk. If I push on the back end of this, which way is it going to go? Is the trunk going to move up? Is it going to go down, right, left? Any guesses out there? No guesses. Come on, guys. Okay. Let's go ahead and let's do the simulation then to figure this out. All I'm going to do to run the simulation is I'll just switch to my Simulation Workspace, and I'm not concerned with testing this to failure. I'm not concerned with doing getting really fine, accurate results from this, to be totally honest. So I'm going to try to run this as fast as possible to get through as many of these examples as I can. I have like 5 different examples I'd like to get to. So we'll select a static study, and as you saw there's 8 different study types available to us. And there's some answers. Okay, good. Jack, did you already see this? Okay. Anyway, so let's get to this, and let's create this simulation and figure out which direction it's going to move. And without even having to print this, I'm going to be able to get some answers very quickly. So I'm going to hit C on my keyboard to turn on my structural constraints, and I'll just fix it at these 2 locations down here at the bottom of this. I mean, if you're actually holding this, you could fix it in some different ways, but all we really want to do is just fix that bottom bit. And you know what? I like to use the orbit. The constrained orbit, and something's annoying me right now. You can notice it's not letting me kind of filter back. I'm going to do something real quick here. I'm going to just set this view as my top. I do this probably every day 20 times to make sure I can rotate things in the way I want. I just really love the constrained orbit. Anyway, so it's been constrained now at those 2 hole locations. Now I just need a force, so I'm going to hit L on my keyboard to get to my structural loads. And I'll select this back end here, and I'll say, 1 pound, doesn't really matter. I just need something to move, and with the deformation scale altered, it's going to give me some information. And just like that, I've set it up enough. I mean, I can look at the material, and it's probably steel right now. It doesn't matter. 1 pound on a 1/4 inch plate steel is probably not really going to move stuff. But in terms of getting the results I want, it doesn't matter because, as I mentioned, we should be able to see the displacement plot, and it's going to illustrate to us which direction the trunk is going to move in. Okay, so we solved it. We can see our results here, and instead of looking at stress or safety factor, obviously those are all pretty negligible. But as we get into displacement, now we're actually starting to get an idea of how this thing's going to move. And to get a really clear idea, and by the way, if you're looking at any simulation results, do note the scale, right? What Fusion will do automatically is it's going to adjust the scale so you can very clearly visualize what's going on there. So if I hit S on my keyboard here, I can change it to the actual deformation, which you can barely tell anything's happened there. Instead, I can go to the adjusted 5 times, and you get a much more clearer understanding of what's going to happen there, and some crazy things are happening, like it's interfering. So typically I'll use the adjusted, just the normal plain adjusted. It does a pretty good job of finding a happy medium. And then from here, and you'll notice I use my S key quite a lot, and I've added all these to this to make it a little bit easier to access them. Otherwise, you'd change your tab to your results, and here you'll find the same options, right? But what I want to do here to really understand this is we'll go to an animation. I like to turn up 50 steps, and we'll go 2-way, and I'll also set it to the fastest. So I'll hit play, and you're starting to see and get an understanding of where that trunk moves, which is it's not. It's actually going to stay stationary. And this works in a lot of different load directions and a lot of different cases. Like, I can go ahead and clone the study, and maybe I want to try a different force here or a different direction. Maybe I'm going to try to trick things here. I'm going to flip it around and, run it again. And you'll notice that I'm running this locally. For simple cases like this, 100% your solve is going to be much, much faster if you actually do it locally. If you do it on the cloud, it's going to have to upload and then it's going to have to download. And for a simple problem like this, 100% run it locally. You're going to get your answers back faster, and you're going to save a couple cloud credits as well. So let's go back to my screen, and here you can see it solving real quick again. And so now it's being pulled the other way. Let's go and switch that back to displacement again, and look at that, it's still going to stay stationary. So that was a nice little trick question, obviously. The way that these pivots are made and the way that this model is set up, you can apply loads any which way on that tail, and it's going to stay very, very stationary at that case. So my recommendation to you is, print this up, show it to your friends, ask them the same question, and you got a little trick you can play on them. So that does it for the elephant. Another model that I thought was really neat, and I'll build this one again from scratch, and we'll come back to those pliers a little bit later. In this case, I do again have a DXF, and I'll select the face that I want to drop it into, and I'll find the DXF, and in this case, it's going to be in my compliant mechanisms, the Ortho-planar spring. This thing's pretty neat. Again, in this case, they provided a DXF and an STL, so you can go straight to printing if you'd like. This is a pretty neat little case, and I believe they have a video that I can show you real quick. But in looking at this, you probably get a pretty quick idea of what it's going to do. And let me switch to their website, and let me just quickly, they have all kinds of really cool stuff here. Shoot, I must have been on a different page. Well, darn it, I forgot where that link was. Anyway, what this spring is going to do is, if you look at it, it's going to enable us to resist moving up or down, right? If you make this out of steel, you're going to get a nice little spring. If you make it out of ABS, I think people will use if they're creating like plastic style springs or printing springs, you're going to be able to resist some movements in some different ways. And this is not your traditional spring that you think of. So I'm going to do something here. I'm going to extrude this up. In this case, I do want to make sure to include the areas in the B there. It's not really going to affect my results too much, but it's something that I'll pay attention to. And I will set this distance to 1/8 of an inch in this case. So there we go. Now that's it. That's the design's ready to go. Now I can start to get some simulation set up. So I'll switch to my Simulation Workspace. And again, I'll use a static stress in this case, but there's some reasons why you might want to consider using a different study type, and I'll touch on that a little bit later when we switch to kind of the more finished version of this. But I'm sure everyone here understands what a spring rate is. It's it's essentially the proportion of force required to move a spring a set distance, and because I'm in inches once again. We're going to do this with pounds per inch of movement. So that's what we're going to try to figure out here. We'll switch back to my screen here, and one way to try to figure out how. Oh, there's Robert. Robert's the one who doesn't like it when we use inches, and so he's going to be mad at me for using inches. So anyway, what I was going to say is I'm going to constrain this very quickly. I'm going to hit C on my keyboard, and I'm going to fix that internal cylindrical face. And then on the outside, I'm going to apply a load, and I can apply this load to the outer ring as well, or the outer cylindrical face. And I'm going to move this. Actually, I'm going to do it upward. And try to figure out the spring rate for this, I'm going to set this to 1 pound, and I'll click OK. And I'll also want to pay attention to my material, right? So, there's various types of materials you want to use for springs. I mentioned ABS, if you're going to try to print something like this, is probably a good fit. And like a 1080 steel, if you're going to actually make this out of metal, because you can mill these, obviously, right? You can do this on a laser, water jet, whatever you want to use. But I'm going to go and I'm going to change this material, and let's select something a little, more appropriate. Let's do this 1080 steel. Now, what I did there, and I don't think I brought enough attention to it, so let me jump back into it. I fixed the inner ring, and then I applied a force of 1 pound. And the reason why I'm doing that is because it's going to make it very simple for me to calculate what the spring rate is for this. So I'm going to go and I'm going to solve this locally once again, just to cut down on that solve time and to get results back faster. And we should see this back in a very short amount of time here. But so what I'm going to do here is I'm going to take the results, and they're already back. I changed to my face so I could talk to you for a second, but the results are that fast. It's a very simple problem in terms of what our computers can do these days. But that 1 pound of force, what I wanted to do is I wanted to look at the displacement, and from this I can go and I can proportionally figure out what force is required to cause the 1 inch of movement to get that spring rate out of it, right? So one thing you do want to pay attention to here is you don't maybe necessarily want your total displacement. I mean, it should be relatively close. What I'm more interested in, and because this is an ortho-planar spring, it's moving up and down, I'm really interested in that y displacement. So I'm going to change that to y, and as I mentioned, it's really not going to alter things. But from this, I'm going to go and I'm going to figure out what force would be required to, and I'm writing down this value so I can show you this very difficult math that I'm going to be doing here. From this, I'm going to proportionally figure out what this is. So I'm going to say 1 divided by that value, 0.002773, and that is going to tell me it's going to take 360 pounds to get this to move the full inch, because 1 pound of force moves it, 0.002773 inches. So do a little bit of math, and you've come to this value. Now, that's not the only way of solving this, right? There's actually some more elegant and faster ways of doing this. Let's go ahead and clone this study. And in this case, I'm going to get rid of the force. I'm going to delete this guy out, and instead I'm going to go and I'm going to create another constraint. Yeah, you might be questioning why I'm doing another constraint here, but the reason why I'm going to go to this constraint is because I'm going to be able to use a prescribed displacement. By using this, I'll be able to say, once again, I want this outer edge to move down or up an inch, and I'm going to have it go up an inch just to stay consistent with the previous example. So we'll set that as 1. We'll click OK, and we'll solve this again locally. And in just a short amount of time here, we're going to be able to very quickly extract the value here. Don't be surprised if there's a little bit of difference here than the other one, but the way that I'm going to be able to extract this, and by the way, I do want to note that is not an inch of movement, right? That's part of that alteration that happens to make things a little bit easier to see, and sometimes it exaggerates things, and sometimes it actually scales back the amount of movement. If I move this back to like the actual displacement, you can see, yeah, that's more closely that's more likely an inch, right? If this is an 8 inch thick, then that's what I'd expect to see happen, right? So how we're going to actually extract the value for the spring rate here is, instead of looking, because I didn't apply a force here, I just forced it to move, I'm going to have to figure out from the reaction force. So I'm going to pull off my reaction, and I'm going to do this from the fixed face. And here you can see it's going to be about 418 pounds. So that's actually pretty significant difference in the other one. Somewhat significant. It's like 60 pounds compared to the other one. What could have caused that is the number of significant figures, 0.002773. If I had carried that out further, hopefully I'd get closer to this number, but there is a little bit of difference there to take note of. So in using this method, you could print this with ABS. You could figure out like an exact thickness that you want your spring to be in order to get the amount of resistance that you're after. But I should note that with this amount of displacement, it's really actually better to solve this with a nonlinear study. So I'm going to clone this study once again. I'm going to go up to my settings here, and I'm going to say, hey, I don't want this to be a static stress study. I want this to be a nonlinear static stress study. This is a much more accurate solver. It's a much slower solver, but the reason why it's more accurate is because it actually breaks down this into the pseudo time, into these smaller increments in order to recalculate things like stiffness matrices, and it's going to recalculate load direction as well. So if your load direction should change to update with how things are deforming through the solve, and this is something that is crucial to getting accurate results. So here I could set this to 10, and I'm ready to go solve this again, right? So I don't need to go and I don't need to set it up again. I can just send it to the cloud to start solving, and I built my solve into here as well. And you cannot solve these locally, right? So you're gonna have to solve this one in the cloud, and I can say, hey, pull from this one, solve one study, and I can come back and review those a little bit later. But I've actually already taken the liberty of solving this a couple of times, and so I did the same thing. I did it with ABS, and I did it with the spring steel. So I did the exact same thing. I applied a pound, and then I did a little math to figure out the proportional spring rate, and then I did a prescribed displacement to figure it out again, and then I did the nonlinear versions as well to start to see some more results here. I don't know why my results are out of date there, but this is actually a thicker version. This, I believe, is, well, maybe, I'm not sure what this one is, a quarter of an inch or something, but you get an idea, and as this goes through, in this case I actually moved it downward, and that's why I swapped it up, because I was looking at the displacement in the y direction. I prefer it being positive. As I scroll through this, you can get an idea of what's happening through this solve. Now, what's really cool is if you go through all this, and maybe what you're trying to do is you're trying to figure out the precise thickness you want to make a spring for some certain application. What you can do is you can jump into the Simplify workspace. You can clone this simulation model. It's going to pull over all 6 of these studies that we've already created, and maybe the spring was not resistant enough, or maybe it was too resistant. All I need to do is do a press pull here to like add material or subtract material, and you'll get some very different spring rates, right? So I'll just move that down a little bit, and I can solve that again, and I can get a very quick understanding of what the new spring rate is after sending these off to the cloud to solve. Okay, so that was, I hope everyone learned something watching that. I'm trying to watch some of the comments, and hopefully it's all pertinent and stuff that you're going to be able to use in your day-to-day. The next thing I wanted to look at was the switch. These were really neat. These are these bistable mechanisms, and if you've watched the video, basically push down on, and I'm not showing my screen, let's show my screen. So if you push down on this side, it's going to like snap into place all of a sudden, right? So and then you can push it back the other way, and it'll snap back out of place. And pretty neat stuff. It's all related to like the stability of this system, and how these things kind of fit together, and the pivots and all that. That's a very simplified explanation of how and why they work. The other one was this guy, which a lot of people I've seen on Thingiverse for printing, and they were all saying how cool it was. I recommend, if you want to play around with these, this would be a good example for you to take a look at. But this one's really neat, similar due to all the pivots and The way that this is modeled, then if you push it down, it's going to like stick and it's going to snap into place. And if you push it back, it's going to snap back into place on the other side. Now, I'm not going to solve these ones in front of you because they actually require a different type of solution, a different type of study, which is going to take even longer. One thing that I would note about some of these is in this case, this is a case where I solved it with the static study. So I'm going to just, maybe we'll just animate this real quick so you get an idea of what's happening here. One limitation of the static solver is that the load direction doesn't change. So, it's pointing down and to the right at first. And so as it goes through the solve, as it goes through the solution, it's like pulling it down to the right, which really isn't accurate. If you're really thinking about this thing in real life, you're just going to push down. It's that force is going to stay consistent, kind of curl around about that. So this static stress study is not really giving me accurate results. So instead, I could have gone and done this with a nonlinear study, and here was the first go that I did. And what you'll notice here, and I believe this is the actual displacement, so yeah, I'm just going to verify that real quick. As we get into like the 50th step here, you can see it goes from like moving very slowly. And one thing to note is that with the nonlinear studies, the load is just being incremented up per your solution domain. So over the 50 steps that I've solved this over, it's just slowly adding a little bit more weight each time. As it gets towards the end here, it's going to snap. It's going to really, it's that stability, right? So it's going to just drop into place. But one thing it doesn't do accurately is it doesn't find the contact, right? It doesn't realize that it's running into this piece or it's not running into that piece, and so those results are obviously not correct. If I look at the way that I set this up, and there's a really important reason why I did this. If I go to like my simplify dialog, I actually took the model and I drew a couple lines through it and I split bodies out. So instead of having one single body for the simulation's sake, for the nonlinear simulation's sake, I split out various pieces. And in doing so, it's going to enable me to have a little bit additional control over how the solution is come to, and how things are going to react with one another. I said I wasn't going to do that. So that's not accurate. So what I did in the next case is I increased the mesh density. So one way to try to overcome not finding the contact there is to increase the mesh density, and hopefully that's going to help to recognize when things are starting to collide with one another. All you need to do to increase the mesh density is go into under Manage, Local Mesh Control. There you can select faces, or you can select edges, or you can select entire bodies if you wanted to use that to increase the mesh. And in doing so, it's going to, in this case, it actually was able to find that contact a little bit better, so pretty neat. I just love how this is just doing a really good job of reacting the way that I'd expect. And we can start to pull more data off of this with both like our event simulations and our nonlinear simulations. I'll show you an event simulation in a second here. You can actually come in and see the plot through this pseudo time, or through the steps that we solve this in, and you can see where it starts to become unstable is about the 35th step, and then that's when it just kind of gives out, right? So from that we could go back to our load cases and we could extract what is the exact force that is going to cause this thing to switch. So really neat. And by the way, this was added probably about 3-6 months ago or something. But what's really cool is from this, you can actually go right into probing and creating a probe at a very specific point, like where I'm really interested in measuring displacement is probably that point right there. And in doing so, it's going to give us the ability to kind of interact with this data a little bit better and give us an idea of what we're seeing there and extract out a little more information. What I would recommend, by the way, when you're looking at the plot here, as I'm doing right now, is to synchronize the plot with the graphics. So if you hit that little lock right there, as I now scroll through this, you can actually see the movement happening in the background there, and so we're getting a little bit better idea of what's happening. Okay, so hope that's handy. The other way I solved this was with an event simulation. So I'm going to switch to Sim Model 2. Event simulations are basically nonlinear simulations because it can do the nonlinear materials. It updates at every increment, at every step. But in addition to that, it's actually going to solve with a real time domain. So it's really going to enable us to extract more pertinent data. So the other neat thing about this is that its contact is very simple to work with in that you can actually have self contact. So if I go to my contact sets here, you can see by default it's going to do this global separation contact, which again is more accurate contact style for most cases. But that allows self contact is something that's super handy for something like this, especially, right? Because it's going to update and it's going to figure out if it starts to run into itself. So here's the first simulation that I ran. You can see it kind of pops down and then it pops back up. Now, the other really neat thing about this, as I was mentioning, is that the time is, real time. And in having that ability, we can actually go in and apply this load in different ways. So the reason why it snapped down and then maybe snapped back a little bit is because I came in here and I applied, zero point 0.6 pounds about very quickly, and then I kind of slowed the application because what I was trying to capture was, I was trying to figure out what load was actually going to cause that instability where it actually finally snaps. And what you should note here is that we're not calculating this over a very long period of time. You're not doing these for 10 seconds. You're not doing it for 15 seconds. You're doing it for like 1,000th of a second, or in this case, 100th of a second. And this is just the nature of event studies because they are very complex. The mathematics behind them take quite a long time to solve. And if you were going to try to solve something like this for 10 seconds, it wouldn't solve. I mean, Fusion's solver will time out after I think 12 hours. If it determines it's going to take that long to solve, it's going to just pop you out and say, hey, we don't have results for you. So one way you can go and alter things like the details that I was showing you there is go into your settings here by selecting from the toolbar of Manage. And here's where you define your study types if you've already created one. Oops, sorry, gotta show my screen. So here you can see this is where you can adjust the event duration. The other thing that I'll do here often is I'll turn off the element deletion. While that looks cool and while it's gonna enable us to see things like really failing, coming to that ultimate failure, for this case I really just want to kind of figure out details about what kind of force is required to get this switch to actuate. Then this is something that I don't want element deletion on because, as you might have seen, the factor of safety is very low. I think it would have already failed or something. So turning that off is going to enable me to get through that. The other thing I'll do here is maybe I'll increase the number of result intervals because from that I'll be able to interact with the data at the end a little bit better. So that was the first one, and the next one I actually kind of did something else here. I think it was similar. Let's look at my load, and I have so many results. I forget what I was doing in each one, but in this case I kind of ramped up the load to again try to capture and understand, at what point does it snap, and this is one of these things that we can deduce from looking at these results, and you can see, right around like the 10th step or right around the highest value force, then that's where it starts to lose stability and really snap down. And in this final case, I was playing with something. I was actually applying a force in one direction and then reversing it. In that case, I unfortunately didn't apply enough load to get it to snap down and then snap back. So here you can see, oh no, sorry. And this one, it just went up and then snapped. So when you look at event simulation results, sometimes you'll see a lot of movement. And again, this is the other thing that's happening with event simulations is there's damping that you need to consider. And in fact, I don't think I turned on damping for any of these cases that we're looking at here, but that's why you see those vibrations. It's actually considering, what happens when you pull something and let go, some elastic thing, right? So it's gonna give us a lot more results, and that's why sometimes you'll see some weird things happening there. In this case, this is where I actually applied the force in one way. So here's just the first example where I wanted to, figure out the force causing it to go down, and that's where it really shakes out. Because if I look at this load case, I apply the load early in the solution domain, and then I like to take it off to kind of figure out what happens after that, because a lot of times you'll use event studies to like figure out what happens after an impact or something like that. So you'll apply the load very quickly and then take it off completely and just see what happens with the system. And that's kind of what we were looking at in this first example. Getting a little bit of spinning action there. This is running these live streams. It takes a lot more from your system than you'd expect, but we'll get through it. Fingers crossed. There's a couple more studies that I wanted to show you here, but this is one of these cases where I applied the force in one direction and then kind of reversed it, and I wanted to see it switch back and forth. And again, remember, this is over an extremely small time frame, so something to consider. And let's see what's going on here. I'm going to do a little song and dance while that's coming out of whatever's going on there. I mean, I've run 4 or 5 simulations so far. I'm loading these results that are extremely complicated and massive. Event study results are like in gigs. It's not measured by megabytes or anything. And we're running the streaming software, which is causing a little bit of slowness here. Did I say to solve here? I don't know what's going on here. Well, that might conclude our presentation, unfortunately. We're actually kind of coming to the end of this. So let's just wrap it up. I can't do a song and dance for that long. I hope everyone learned something. There's quite a lot you can do with our simulation. There's 8 different study types. I showed you running 1 or 2, but there's a lot that goes into setting up an event study. For some of those cases, I ran through 20 iterations before I got to a solution that I was satisfied with, and part of that is these systems are completely new to me. I don't know what kind of forces are required. I don't know what materials we're working with, and there's a little bit of that play of like figuring out, do I need to split the body to find the contact, or there's other things that I need to do as well. I did want to plug, Brad is up next Tuesday. It was originally going to be Bryce doing a drawings presentation. Unfortunately, he had other conflicts, so he's now going to do that, I think, later in the month. I think on the 16th. You can check the schedule on our YouTube channel. I hope that was handy. Hope everyone learned something. If you have questions, post them under the video after completion of this. It's hard to kind of go back and look through all the chat and figure out what questions need answering. So if you do have questions, go ahead and post them under this video once it posts. It takes a second to process before it gets up there. But again, thanks everyone for your time. I hope everyone learned something. Have a great day.